the supporting facts. We treat those supporting facts associated to the question as the premise, and we treat the question answer pair as our observation. And in this work, we would like to ask the LM to recover the agentic trajectory that can help us to get to the answer. So what is the trajectory here? So recall what we have done in the Muzhi work. So it contains the initial plan P, the planner reasoning thoughts in each step, the set of sub-questions or search actions issued by the planner to be executed in each step, and the corresponding author of each sub-question, and the reasoning thoughts to generate these to reasoning thoughts to analyze those retrieved contexts and to generate those answers of each sub-question. So our question becomes how to produce such kind of trajectories. So our proposed method have three stages. In the first stage, given the question, the final answer, and the guidance from the supporting evidence, we can reverse engineer a dependency-aware plan that decomposes the question into sub-questions, forming a latent reasoning graph. So actually, we do not need to draw this graph out, but we can make it into decomposed and executable subtasks. For example, this question is a three-hop bridge comparison question. So based on this question and the golden supporting evidence, it is very easy for an LM to come up with the plan. So if it is still difficult, we can have a similar question as an in-context example. So then we ask the LM to produce the search action for each step. It is just similar as the Muzhi workflow, but the key is the planning process is guided by the supporting evidence. So in the second stage, we aim to solve each sub-question and construct the reasoning path for the executor side. However, there is a challenge. So in real-time retrieval, the dense or sparse retriever may miss those golden evidence. Since the dataset itself does not provide intermediate answers, so imperfect retrieval can break down the complete reasoning trajectory. So in case, instead of performing real-time retrieval for each question, so we use the full supporting evidence pool to build up a proxy, or we say the simulated environment. So here in this environment, we can ensure the LM to access to the evidence to solve each sub-question. So specifically for each sub-question, we first derive the intermediate answer using all golden evidence associated to the original sub-question. Then we use a sentence transformer to encode that intermediate answer and each of the supporting evidence associated to this question. And those evidence with a high cosine similarity, will be considered as the evidence for this specific sub-question. And finally, we ask the large language model to generate some reasoning thoughts that can help us to identify these golden evidence for this sub-question from the full size of supporting evidences. So the reasoning thoughts and intermediate answers obtained in this stage can help us to teach the LM to reason about retrieved contexts. And this is for executor side. And finally, we convert everything we obtained from the first two steps into training examples. Here, we obtained about 265,000 trajectories from the three datasets, Twiki, HotOpQA, and Muzhi. For each question, our training trajectory contains one multi-turn planner prompt and multiple single-turn executor prompts to teach the LM to conduct evidence-grounded question answer. So with this dataset, we can simply train the large language model with supervised fine-tuning, and this process can equip the large language model with required agentic behaviors. So during evaluation, we do not provide the large language model with any supporting evidence or answers, and we ask the fine-tuned LLM, actually the search agent, to answer the open domain questions. In other words, in test 10, the search agent needs to issue search actions and interact with external environment to retrieve relevant evidence and answer the question. So from the experimental results, we found that if we use our synthetic trajectory to train an 8B backbone LM, and we use this LM to build up an agent, we can have a double-digit absolute performance improvement in terms of exact match. So we also find strong scaling effect. Even 1B and 3B models trained on our synthetic trajectory can become competitive, showing the high. It shows that the high quality synthetic trajectories can offset the limitation of model size. Now, let me summarize the talk with some takeaways. So the first point is that workflow design matters. We show that the planner executor split and structured planning like DAG-based reasoning can reduce the long context reasoning failure. Also, the optimization process can be simplified. So the successful experience of MyGo, this algorithm, it demonstrates that high quality trajectory sampling and supervised fine-tuning style training can match heavier reinforcement learning recipes like GRPO with better efficiency. Also, we found that the training data is the main bottleneck of the search agent development. And we found that our evidence anchor process supervised trajectories provide a shortcut to equip the agentic skills such like planning, to use, and grounded reasonings for large language models. However, building such a synthetic trajectories needs extra support from the question answering dataset. So that's all for today's talk. Thank you for your attention, and I'm happy to take questions.
Yeah, thank you so much for your insightful, inspiring talks. Yeah.
Thank you.
So now let's the Q&A session. Is there anyone has some questions related to this paper?
Hi, I do have a quick
Sorry,
question. Oh, sorry. Professor
sorry,
Lin, do you want to
sorry,
go?
I'm driving, sorry. I do have a lot related to the paper. Because I'm driving, sorry, Qifeng, maybe I'll just ask the question and then you can go after. But my general question is, we have submitted a couple grant proposals that is supposed to do some human-in-loop RLHF fine-tuning, and like they're all different applications, and we've been winning a lot of grant proposals lately. I need to hire someone to do this work. What kind of, like, I know RL is very difficult to fine tune. Like the previous master students I work with, for his master's, after 2 years, it was only like some toy examples for his like auto fine tuning RL method. And it didn't even work very well. So do you think, like, what kind of skill sets or how long do you think? And, with agentic AI now, like, is it still very hard to get it done from the ground up? Or like, do you think a master student can do it, or it has to be like a PhD student who devotes like maybe like a couple years to it?
Thank you for your question. It's interesting, Professor Lee. So, to me, I believe that a master student is okay. So, because now it's year of 2026, it's different from several years before. So
2021.
yeah, it's different from years before. Yeah. So now we do have some advanced machine learning infrastructure. So we have Llama Factory for supervised fine
Yeah,
tuning. So we do not need to build the wheel by ourselves. We also have a
yeah,
VER. So it is proposed by developed by ByteDance. So we believe that many of us doing our research by modifying something upon VRL. So there's also someone performing building search agents upon this platform. So if we can do something based on some existing infrastructure, and it become easier. And now we have something called anti-gravity cloud code to help us to analyze the code structure, because if we check this machine learning infrastructure, it is not very easy to be interpreted, because it's really if we check the code, it looks like a large software actually. So they use some advanced software engineering skills to encapsulate different modules. So yeah, so if we work upon this, it will be much easier.
Right. Thank you. Sorry, go ahead, Qifeng.
Yeah, thank you, Professor, for your question. So we can discuss this later.
Hi. Can you hear
Yeah,
me?
hello? Yeah, of
Yeah.
course.
Yeah. So thank you so much, Muzhi. It's a really inspiring talk. And can you go back to the previous slides? The one that's you have no like the yeah, this one. So I'm just curious why. So for multi-realm planners, like how did you decide the number of executions and the this whole process? Like you said, like it's illustrated over there. There are like four rounds. If I understand it correctly, are they linearly or it's like yeah.
Oh, yeah, thank you for your question. So, uh, I believe you are asking why we use three iterations, or why we have three planning steps, and why we have four execution steps.
Yeah, yeah.
Is that your question?
Yeah,
So yeah,
also, are they linearly or like in loop or
okay. Thank you for your question. So it depends on the question itself. So so yeah, we do use a trick in constructing these synthetic trajectories. So for questions in hotspot QA dataset, two-wiki dataset, and music dataset, there's 9 or 10 different reasoning types, or we call it question types, and we have 9 or 10 different reasoning patterns. For different reasoning for questions with different reasoning patterns, we have an individual, we have a different uh, example for the LM to follow. So before asking the LM to produce the answer, to produce this specific plan, we have an in-context demonstration for itself. And the in-context demonstration, it has a question which is very similar with this question in terms of the reasoning pattern, in terms of the reasoning pattern. And this is the first thing I would like to say. And the second thing is that because we provide the LM with the supporting evidence here, so the LM already know the supporting evidence when constructing the prompts, or we say the reasoning trajectory. So we in our prompt we ask the LM to to parallelize those subtasks which are independent subtasks. So, for example, here, if we ask the director of one movie, it is not necessary to know the director of the other movie. So that's why these two steps can be finished within one single iteration. So that in iteration one, we issue two different search actions, and it is actually one executor, but you can think about using two different executors to retrieve the context for the two uh, to handle the two sub questions actually. So that's why we have three steps, because it depends on the question type and depends on the analysis conducted by the LM to process those supporting evidence. So that's why we have three steps here.
okay,
And one,
thank
yeah,
you. Yeah, please continue.
yeah, thank you. So So we do not have a loop here. We do not have so-called a loop, but we have different iterations to solve the problem. So in each iteration contains a planning step and an execution step, and after that, the planner will get the results from the executor, and it is required to issue uh, more search actions based on the results if necessary. This is during test time and during the data construction time. So it will receive the guidance from the supporting evidence. So it already have a global view to know how much step we need to solve the problem because it already have the all the evidence to solve this problem. That's why at first, initially, it already know it needs 3 steps to solve this problem. But this is different from the test time. During the test time, it does not have any supporting evidence, so it needs to uh, make the decision dynamically by itself.
Okay.
I
Okay.
yeah.
Yeah. Thank you. Thank you so much.
Thank you for the question. I would like also to mention a small part. So if we during the construction of the synthetic trajectory, we can actually use a different LM than the one we are using, than the one which will be trained. So we can use the 70 billion uh, Kuhn or Llama model to construct the synthetic reasoning path. And for a larger model, the task will be easier. So our basic idea why we are going to use this supporting evidence on the answer is to make the reasoning process or make the data synthesis process much more easier for the large language model. We provide the hint we have, all of the hints to the LM, and we can use a larger LM to produce those synthetic trajectories. And once we obtain those synthetic trajectories, we can use them to train a smaller scale module, and this small scale module will be much stronger after training. Yeah.
Yeah, thank you so much, Muzhi, and also Chief Fine's questions. Is there anyone else want to ask?
I have a question. Um,
Yeah, go ahead, San Diego.
Yeah, please.
well, thank you for your presentation. I feel it was very interesting. Uh, but also I wanted to know, I've seen that there has been a lot of like research agent frameworks, like I don't know, like deep agents. I've seen a couple other tools that try to, well, they focus on other stuff, but mainly they want also to build frameworks. Have you thought about maybe comparing your framework in several tasks against other workflows? Um, have you done it? How or what are you planning to do it? Um, like with I'd say like a complex workflow.
Uh, Thank you for the question. So, yes, during our experiments, we do compare our method with a different reasoning workflow. For example, in this work, we compare our LV path with different RAG agents or search agents such as Search R1, Search R1, R1 Search, etc., etc. So, however, I'm not going to say that my search agent, the workflow, the design is better than the other or something. Yeah. But what we can, because different workflow, they have common design choices and like that. So what I want to say is that we can uh, integrate several useful design choices together to have to design a new search agent or a RAG agent or some other agent for different tasks. So for QA, so we know that so different sub questions may not be mutually dependent, may not be dependent. So we can handle those independent sub-questions in parallel, and this can help us to reduce the reasoning steps. And we also have the planner executor steps because uh, why we would like to have such kind of design choice because if we pass back all of the retrieved evidence back to the planner, and the context of the planner will be longer, and longer because it will include all of the retrieved evidence in each steps for each sub question. So therefore, after that, the context will be very long, and we know that the long context reasoning capability for the LM is not that good, not that desirable. And also, there will be some irrelevant context within the supporting evidence, and then the LM will lose its it will uh, lose its original target. It will lose its original target, and finally, we cannot obtain the correct result. We can borrow. Actually, my point or my experience that we can borrow different kinds of design patterns from different authors or different search agents, and we can use them to build up a new search agent. And I believe that in 2026, in this year, someone uh, our focus is more like to be on the harness part. So yeah, so we can keep track of this part. I hope this answers your question.
Yes, thank you.
Thank you.
Thank you, San Diego. Thank you, Muzhi. So, thank you very much, Muzhi, for the insightful and inspiring talk you shared today. We really appreciate your time and effort in sharing your recent work with us, especially your explanations of RAG workflow design, evidence-grounded in reasoning trajectory synthesis, and lightweight reinforced learning for LLM search agents.
Yeah.
Uh,
Yeah, thank you for and Muzhi, if you can say thank you and say hi to Professor Erwin King for me and say yeah, it's been decades, but just thank you for his hospitality at CUHK.
Probably I will say thanks to him, and thank you very much for your kind invitation, for you and for Jinxi. It is my pleasure to be here today to see all of you and to discuss the research with you. Yeah.
Yes, thank you so much. Your talk gave us a clear understanding of how more reliable and scalable search agents can be built for complex question answering. Thank you again for joining us today, and thank you everyone for attending.